Okay, all the participants going up now. Okay, evening all. So what we'll do, whilst the numbers are still going up on the participants list, we'll just sit tight and we'll just keep chatting. We'll probably aim to kick off once the participants start to plateau. So in the meantime, if you've got any questions, put them in the Q&A section. Linda will be collating those as we move along, and we'll answer those at the end of the presentation. If you just want to post and put comments in, feel free, just drop that into the chat. But it'd be good to find out where people are from tonight, where people are dialing in from, because we have had people from far-flung parts of the globe dialing into to glorious South Yorkshire. So do feel free to let us know where you're from, and we can just generally get a feel for it and see what sort of reach we're getting really on the presentations. So we've got one from Dublin, that's good. Hampshire. Oh yes, Bart Green's always good. Oh, we're flying in from all over the place. So we've got Sweden there. See Steve sneaked in at Bristol. Denmark. Oh. See London coming on. Okay, well, the numbers are still creeping up on the participants list, so we'll just keep talking. Oh, Scunny Bunnies are on from British Steel, very good. My old stomping ground. We've got a real good spread today in terms of where people are coming from. There's Bangor, we've got North Wales in. So it's looking like, oh no, there's still people coming in. See Grinstead's in again, it's very good. Oh, there's loads coming in from Bristol now, very popular place. Don't think we've got the Americans on today. Don't think we've got the Aussies on today either. Somebody's going to correct me. Oh, we've got a winner there. We've got Dubai on. Got from Doncaster to Dubai today. Okay, so I think numbers are starting to plateau at the minute, so I think we'll make a start. So just to introduce us, this is the South Yorkshire network from the IET, and this is the fourth in the electrical safety management series that we've been operating. So we kicked off with Viper Innovations, who gave us a briefing on their Cable Guardian product that was intended for continual monitoring of line-side cables on the railway and really any sort of distribution, low voltage distribution cables. We then moved on to Mike Frain's previous presentation that gave rise to this one, where he gave us a broader overview of managing the arc flash risk in the workplace, particularly looking at in-service switchgear. Ian Naylor gave us a presentation then looking at safety management of switchgear, probably from a point of view of designing out problems at source. But backed by popular demand is Mike. I mean, it's fair to say that these presentations have created quite a lot of discussion in the background. And as good engineers do, we've all chucked our 2 pennies in as to what we believe is right, wrong, or indifferent on the subject. So Mike's come back to straighten us up, frankly. So here's where we are. And I think with that, I think we'll just hand over. Just to finish it off, we'll cover Q&A, as you said, at the end. Linda will just continue through the presentation, dropping in if we need to, offering hints, tips, that sort of thing. If there's any sort of common questions, we'll try and deal with those in a common phrase. Mike does tend to pick these things up and answer them personally afterwards anyway. So if you don't get answered on the day, there's a possibility we can get answered afterward as well. But what we'll do when it comes to the end of the presentation, then I'll just say a few words to finish it off with, and we will, or we are, recording the presentation again. Okay, so Mike, over to you.
Thanks very much for that, John. And thanks everybody for being here. Hi everybody. It's another international event by the sounds of it. So if I say good morning, good evening, good day to you all. My name is Mike Frain, and it's my pleasure to take you through this presentation and on why we do our arc flash calculations. Just a small amount about myself. I've been privileged to work with an abundance of household names in most industries. But more than that, I've been so fortunate to have worked alongside people who have contributed so much to electrical safety around the globe, and to make long and enduring friendships along the way. So truly blessed in that regard. Just before we go on, I'd just like to mention at this stage a project that's consumed much of my time for the last couple of years. Apart from volunteering for the IET, the BSI and the IEC as the nominated expert, mostly on arc flash. It's called the European Arc Guide, and it's the vision is to make arc flash management accessible to European engineers. It's done by informing and influencing duty holders, designers and service providers to reduce danger from electrical arcing by providing quick, simple, accessible and accurate tools. It's coupled with expert advice and impartial practical advice. I'm very proud to announce that the guide, including the calculator, is ready for launch very shortly. And you can pre-register for access for the first 7 chapters actually of the guide. And I'll tell you a little bit more about how to pre-register later. Just quickly go down the agenda. I'll start by doing a recap on the calculations. I think it might be something that people have covered before, but maybe not. What they are and what they tell you basically. As promised in the title, I'll go through 10 good reasons why I feel that electrical engineers should embrace the calculations and manage what can be dangerous and destructive arcing faults. Then it's my very great pleasure to tell you about the launch of a new fact file from the IET on the subject of arc flash risk management. Many people have been asking about it for some time. And then the launch of the European Arc Guide that I've been working on with a suite of calculators which will help realise the vision that I gave on the previous slide. And at the end of this session, there'll be time for questions as well. So the first item on the agenda, arc flash calculations. Well, the first thing, Peter Drucker said that you can't manage what you can't measure. And that's how the saying goes. And I've felt that's been the case as far as risk assessment has been concerned for quite some time. The IEEE 1584 guide for performing arc flash calculations is probably the most comprehensive means to evaluate the arc flash hazard, and is internationally recognised as an auditable standard. And whilst there are other methods described in my guide, I'll concentrate on the IEEE 1584 for today. Firstly, the IEEE guide will tell you how to calculate the arcing current. It's very important if you wish to design out the hazard on electrical equipment. From that, secondly, it'll calculate the incident energy, which defines the severity of the arc flash at a certain distance in joules per square centimetre, which it happens to be the true SI unit, although it's popularly expressed in calories per square centimetre as well. So 1.2 square centimetres or 5 joules per square centimetre applied to the skin for 1 second is a threshold at which there could be an onset of a second-degree burn. And it's this figure that's used for determining PPE requirements and the arc flash boundary. So lastly, an arc flash boundary can be calculated, at which the incident energy is calculated, and it's to be reduced below the figure of 1.2 calories per square centimetre, or 5 joules per square centimetre. So that's that magic figure again, the onset of a second degree burn. The IEEE 1584 guide does not include any recommendations for PPE to mitigate arc flash hazards, and they're therefore excluded from the scope. The first thing that the calculations will tell you is the value of arcing current. It'll not come as much of a surprise to find that the arcing current will be lower than the available prospective short circuit current because of the impedance, actually. At high voltage, this attenuation is very much less than at low voltage. You can see that in this graph, which shows arcing current against a prospective short circuit current for 3 different electrode configurations. Firstly, for a 10 kV system, which is at the top of the graph, the straighter lines, and then lower down is for a 400 volt system voltage. While you're extremely unlikely to experience fault levels at 50,000 amps at 10 or 11 kV, the graph just serves to make a comparison, that's all. To know the level of fault current that can flow into an arc is an essential piece of information for the designer who wishes to know whether his electrical protection systems are going to clear an arc fault quickly, safely, and without damage. Or, as a good friend of mine always says, it could also be sometime next Tuesday. What this graph also says is that will the overcurrent protection clear dangerous arcing faults? After all, most calculations are based upon prospective short circuit current only, and automatic disconnection times for shock protection only as well. So more on this a little bit later on in the presentation. Just flick through these. This next slide illustrates the incident energy exposure when carrying out the calculations, the working distance used from head and torso to the prospective arcing source. Next is the arc flash boundary, and this is the distance from a prospective arc source at which the incident energy is calculated to be 5 joules per square centimetre, or 1.2 calories per square centimetre. That's what we mentioned earlier. So what affects arc severity? Well, the first thing is arcing current, and that is governed by the impedance of the supply source. The next is time, and this is the time that it takes for the protection systems to recognise a fault and also to disconnect it. In both cases, severity is directly proportional. So if you double the current, you double the incident energy. If you halve the time to trip, then you halve the incident energy, and so on. So what else affects severity? Well, the first thing is distance. So the relationship between distance and incident energy, it falls exponential actually, and it's good reason to increase distance between a worker and prospective arc fault, and is often used as a risk control measure. Next is the conductor geometry and containment. And firstly is the configuration of the electrodes. The second is the intensity of an electrical arc is a resultant of the level of incident energy is affected by that electrode configuration. It's also horizontal and vertical conductors can create increase or lower amounts of thermal energy. There's also the open arc versus an enclosed arc. On the right-hand side, you can see an enclosed arc and roughly what the test setup looks like. In that particular case, that's called a VCB type of arrangement, and the conductors are V. That's why they're mentioned as vertical, and you can see that the actual thermal energy is forced downwards and out towards the worker in more intensity than you would in an open arc system. So I'm not going to go into this in a great deal of detail today. Last time I put this slide up, I talked about it in a bit more detail than I'm proposing to do today, but the consequences of an arc flash are much more than personal injury or death, if that's not bad enough. But you don't actually need to inquire much further than a quick internet search, do you, to reveal masses of material, including photographs and videos depicting horrendous arc flash individuals that have happened to individuals. But put it simply, electrical burns are nasty. They're very slow healing and leave lasting physical and mental scars. Just recently, in the next line on prosecution and fines, there's been a number of high-profile prosecutions, certainly within the UK, topping £1 million plus costs. And some of those are for low-voltage systems. And it doesn't stop there. Working with a large M&E contractor, it became very clear to me that a recent arc flash incident could have potentially threatened the viability of the company because of the damage to the brand. So it's not a good idea to be prosecuted for an arc flash if the electrical safety is your core competence, which I would hope that's what an electrical contractor would be. Then there's the losses from severe equipment damage and lost production, which can be eye-wateringly huge figures, and certainly in my experience. Finally, I speak about the environmental damage that was caused by a catastrophic arc flash incident in my guidebook in my chapter on myths and mistakes. It burnt the substation down, but created an environmental issue as well. So finally, I just want to mention actually that in the UK, there doesn't even have to be injury for, I'm not sure there's that many have been carried out this way, but wherever there's an arc flash incident, it has to be reported under the reporting of injuries, diseases and dangerous occurrences regulations, or RIDO, and it has to be reported to the authorities, who may or may not take action on that basis. So here we go, this is why we're all here. These are my 10 reasons for calculations. I'm going to look at how we root out real danger, how we can, by calculating, how we can keep people out of restrictive PPE. There's a risk reduction strategy, working on my own experience. Examples of where calculations would have prevented accidents, helps to comply with the law. I'm going to talk about why I think that 90% of the effort, if you were going to carry out a complex arc flash study, is what we should be doing anyway. So I've got a slide on that as well. Where design problems are averted, providing knowledge to workers, which I see as a bedrock of competence, an essential tool for the designer, and those designers are out there. I'll try and explain how this affects you basically. And then finally, my core competence has been for many years now, say, electrical safety management, and working for blue chip companies doing exactly that from a consultancy point of view. And I'll explain how I think it improves the electrical safety management. So how does it root out danger? Well, arc flash is another hazard, and I've been consistent over the years that a major consideration is to understand it and then root out real danger. If you looked at two panels side by side, which were identical on the outside, you wouldn't know actually which had the tiger or the pussycat in there. So this analogy of the hidden tiger lurking inside electrical equipment, it works well for me, as my prime consideration is the identification, the evaluation of the hazards as the first step in risk assessment. Calculation forces us to have a look at the upstream protective devices. And in the same way as protecting against electric shock, impedance is the enemy of good protection. So we need to consider whether an arcing fault is going to be cleared quickly with minimal damage, or the fault will persist with catastrophic harm to the equipment and anyone stood nearby. And bluntly, it will tell you just how big the bang's going to be. So as I say, if you stood in front of two identical switch panels, you don't know which is going to hold a relatively low level of arc flash hazard and the other one which could be extremely high. So just carrying on with that theme about rooting out real danger. On the left-hand side are two BS88 fuses that have been around for years, much more than I have, which is saying something. But they're 400 amp high rupturing capacity fuses. It's probably the most ubiquitous protection device in the UK and beyond for many years. It stood the test of time. It's actually used worldwide nowadays, and it's growing in popularity for its ability to clear faults safely and very quickly. And it's even proving very popular in the US, particularly with DC systems, believe it or not. The vast majority of domestic properties in the UK is fed from a main which is backed up by one of these. So my home, it will be backed up by a 400 amp HRC fuse. On the right is an incident energy chart, which shows an arc flash severity against prospective short circuit current for that same fuse. For horizontal conductors, which I mentioned earlier, the conductor configuration, in an enclosure, and I've highlighted the fast acting zone of the fuse. However, at faults below 12,000 amps, as you can see there, that's when the severity can escalate very quickly. And you can see that, you know, we're talking about, I'm capped it off there at a 2-second disconnection time actually, and it's over 35 calories per square centimetre. So what does that look like? You know, how severe is that? Well, that's what you would need if you were going to just protect yourself against an incident energy of 35 calories or above. This PPE, it's you know, at a distance of 450 millimeter, I would suggest it's you know, it's very uncomfortable. It's restrictive and expensive. It's probably retailing at about 800 to £1,000. So we need to think out how we can root out danger and do something about it. I'm not anti-PPE, by the way, not in any shape or form. I just think that where we can reduce the incident energy levels, we should be doing, and that's basically what this is all about. So, but the difference between restrictive PP and no PP at all is it's often just a few amps, and this is what I'm trying to put over in this particular graph on the right-hand side. This is a 1600 amp circuit breaker, Durham Smith load line air circuit breaker. We're looking at an arcing fault there of 12,000 amps. And if you can see the instantaneous pickup level there, where it coincides with that, you can see that it could trip in 30 milliseconds at the bottom, or just for an amp or two more, it could be tripping at 1.4 seconds. So what's the difference? Well, if it trips at 1.4 seconds, we're talking about destruction of equipment. You know, we're not going to, it could be critical supplies, it could be in a hospital or something like that, possible prosecution, possible fire, and possible severe personal injury, or alternatively use a suit like that. But that doesn't stop the first four things there. Or if it trips in 30 milliseconds, talking about minor equipment damage, short loss of critical supplies, clean up, put it back, or none or minor injury at that point. Number 3, as a risk reduction strategy. I worked here in 2007, I think it was, 2008, sorry. And it happens to be the largest employer in Londonderry. As you can see, Seagate make most of the hard drives that we have to back our computers up, or ones that I have anyway. And there, it's a large employer, 33 kV supply, 140 electrical maintenance staff and 4 major electrical contractors are employed on that site. I did an arc flash study for that entire site back then. And when we looked at it, we identified high thermal energy levels in 120 control panels just in the clean rooms alone. This is just what they call the fabs. Rather than PPE, we successfully reduced all the panels to below 1.2 calories per square centimetre. And how did we do that? Well, we applied new protection settings to the circuit breakers. We also refed some circuits, because I mentioned earlier how impedance can have an effect. So it can lower the impedance. We can increase the arcing fault, and the paradox is, of course, you increase the arcing fault in certain circumstances, that decreases the time to trip. And in that case, that's what we did in one or two instances. We installed local switch fuses on the side of the equipment. As you can see, the equipment cabinets in that picture on the right-hand side are quite numerous in that particular fab. Or we upgraded MCCBs in the existing panels. There was a lot of square D on that particular site, and basically the square D circuit breakers, when it was built, it weren't quite as sophisticated as a new one, but actually you could do a straight swap. So the new ones had adjustable instantaneous pickup levels, and we were able then to just tone those down a little bit, you know, just bearing in mind the load requirements and motor starting and so on. But the thing that I'm trying to put over here is that it was a fraction of the cost of PPE. Because actually getting PPE for clean room environments like that is very expensive. So that was a major driver, I must admit. But there lies the answer to reducing the risk. If they can do it there, why can't any industrial site do the same? And of course, I've got a good history over the years of doing exactly that. You know, retrofitting circuit breakers, or you know, tuning them down and whatever to reduce the amount of incident energy. Wrote their safety procedures and provided them with the software. It was pointless me, every time they replace what they call a tool in the fab, it was pointless me doing new calculations. I taught them how to do that all themselves, and there've been no serious incidents since. There are several examples in my book, and it comes under chapter 12, myths and mistakes, from from the guide where calculations would have picked the problems up before it caused injury. The catastrophic failure of the capacitor, there's also an environmental injury. And in this case, it's an apprentice who was burned while connecting cables into a distribution board. And all three incidents would have been averted had the upstream protection arrangements have been examined as part of an incident energy study. Or, as I'll show you later, some sort of dynamic risk assessment before people start working on there. And of course, I'm sure you may have picked up that perhaps a risk assessment wouldn't have looked at the incident energy in this particular case, but why he was doing it in the first place. Number 5, it helps to comply with the law. Well, whether it's a European Framework Directive 89391, Workplace Health and Safety Directive, commonly referred to as a Framework Directive, or the UK Management of Health and Safety at Work Regs, or the Irish Health and Safety Welfare at Work General Application Regulations 2007. That's from my colleague in Dublin, I heard, who signed on earlier. The cornerstone of risk assessment means that any employer must evaluate all the risks to the safety and health of workers. Arc flash risk assessments for workers who operate in the proximity or in energized equipment, cables and overhead lines. It's an essential part of the electrical safety management. Calculations give us the means to evaluate the hazard and also means to provide prevention techniques such as automatic disconnection of supply for arcing faults. This slide shows how a risk assessment process fits in, and when carrying out risk assessment to a minimum, we must identify what could cause hazards. So in this case, that comes from the system parameters. In the next step, we decide how likely it is that somebody could be harmed and how seriously. And of course, that comes from system conditions. You know, what's the state of the equipment? When was the last time it maintained? Is the upstream device going to operate anyway? And most importantly, what is it that you're doing there? You know, that is going to increase the likelihood. And then finally, you know, we take action, you know, because to reduce the actual risk. And from my guide, I explain a 4P approach to eliminate or control the risk at that point. When we have the means to evaluate the hazards in a workplace, we must take advantage, in my view. As said earlier, it's a matter of a few amperes that can be the difference between an arcing fault being cleared quickly and harmlessly to a situation that results in catastrophic damage, losses and severe personal injury, just for the sake of a few amps. This is something I've often been told over the years that, well, it's a massive amount of work doing an arc flash study. But my retort to this is that the percentage effort in doing an arc flash study, and I'm talking about a full complex arc flash study, is minuscule in when you lay that at the side of what you should actually be doing anyway. So the vast majority of basic electrical safety system information to do an arc flash study, it's what any self-respecting electrical engineer ought to have at their fingertips. A precursor to an arc flash study is to have a single line diagram. Who shouldn't have one of those? Next is a protection coordination study. And then finally, short circuit studies. Now, as you can see, the amount of effort that's required for the arc flash study is 9% out of the total. Where do I get that from? Actually, it's from IEEE 1584, the previous iteration, which was the 2002 edition. And it looked at those 4 categories and it looked at the amount of information you needed for both for each one. There's about 12 pages actually of the actual information you wanted for each one of those items. As it happened, the minority was the arc flash study. Again, in my guidebook, I describe in the chapter, once again, on myths and mistakes, a fault level study, protection coordination study, and an arc flash study that I carried out for a large teaching hospital about 10 years ago. I uncovered a design flaw where there are two MVA voltage optimization units. So this is heavy duty equipment here. They were installed into a critical care block, and they were put between, I don't know if you can see it there, they're installed between each transformer and the main low voltage 400 volt switchboard. What happened is, by looking into this, I wanted to find out what the dynamic impedance of those voltage optimization units were. And to be quite honest, the results I started getting back, I started to realize that the disconnection times at the LV equipment, even for short circuits, that's bolted short circuit current, or, using prospective short circuit currents, wouldn't disconnect very quickly, let alone an arcing fault that might occur at that point. And of course, there's the other question about what a voltage optimization unit's doing in a new critical care unit. Why would you want to lower the voltage in that respect? By the way, I'm not anti-voltage optimization units. I think they've got their place, but not in a new build. In this respect, I think it was a mistake. It's very expensive actually to correct. But I've got to say that management of the health authority were rightly concerned, and we had many debates about this, about the safety of gravely ill patients. They're the people that are in that unit, and they're the ones that are using that facility. But it was corrected, and those were actually taken out in the end. Number 8. Look at providing knowledge to workers. Well, on the right-hand side there, there's a quotation which shows a scope of technical knowledge or experience that's included in the UK Electricity at Work Regulations 1989, and it's the last 2 items. So it's there's 5 bullets, and the last 2 say the understanding of the hazards which may arise during the work and the precautions which need to be taken. And finally, the ability to recognise at all times whether it's safe for work to continue. I believe that experience and training can make a step change in safety practices to reduce harm from electrical faults. Electrical workers are often the ones that will suffer from arcing faults. And yet, and this is from my personal experience, they know surprisingly very little about the phenomena. For instance, a mistaken belief is that low voltage means less harm, or low fault levels means less harm. It can lead to a false sense of security. There may be others who might remember, or be old enough to remember, the old GEC educational video from the 1960s showing switchgear explosions and how BS88 fuses reduce the damage to 0 by disconnecting high fault currents very rapidly. The video show the catastrophic damage from impressive explosions, and I remember it well. That was in my apprenticeship when I first saw those, and I looked it up, and of course listened to the videos again, and from that I gleaned that the prospective fault currents were the levels of 38,000 amps and 60,000 amps at low voltage. and the fuse links were disconnecting short circuits in less than half a second. And the reason for this is because the fuse links are actually operating within that safe zone, that current limiting zone that I mentioned earlier. But if there isn't enough current to actually blow the fuses at that point, or to rupture the fuses, the opposite can happen. So what I was going to say was, I put a picture of the video on the bottom right there. If you do want to watch it, it's great watching, great video, and just rather than me put a big long string for you to click onto, just search for GEC video HRC and you'll find it, no problem at all in there. The other thing is, on the left-hand side, that diagram, I've put a diagram of what we call SCEB, which is what the contributory combination of skills, knowledge, experience, and behaviours. There, you know, that's a model that uses SCEB, and of course, we know all those four make up competence in one way or another. But if we've got the knowledge about arc flash, perhaps that might influence behaviours as well. So in one fell swoop, there are two areas of the SCEB model that we can use for providing knowledge to workers and increasing competence. Now to designers. When we're looking at disconnecting arcing faults, it uses the same principles as shock protection. You know, what we want to do is to disconnect the fault as quickly as possible if we're using electrical protection arrangements comprising, you know, overcurrent protection, which is most often the case in industry and domestic as well. And it does include arcing faults. And as I've shown earlier, a few amps can be the difference between a safe clearance or destructive energy fault let through. And that does include arcing faults. A few amps can be the difference, is what I keep going on about, can be the difference between safe clearance or destructive energy let through. And predicting the severity of arc flash hazards has become more reliable, basically because of the empirical evidence that is there, where they're doing this in laboratory situations where applying it. I think IEEE 1584 was conducted on 2,000 high power laboratory experiments between 208 volts up to 15,000 volts. So they're a little bit more reliable than they may have been at one time and less theoretical. Number 10, I believe that it improves electrical safety management. Well, how? Well, first of all, it gives a fresh view of policies and procedures. It gives a fresh view of fault levels, looking at fault levels again, looks at protection systems and how much confidence will you have that they will operate. Also, de facto, it looks at strength and capability of the electrical equipment too. Also, maintenance regimes. You know, before you sign any electrical safety arc flash study off, you need to know that you know, the maintenance regimes and the equipment itself is fit for purpose. The other thing, just as far as looking in the first place is concerned, it highlights neglect, which is a barometer of whether electrical safety policies are working or not. And I repeat that. I mean, the worst excesses I've seen over the years, and I've got you know, a gallery of horrors, from going around various factories and commercial networks. I can tell you that you look at electrical safety panels, and one thing that wrecks them is either water or ingress of something else like that, or electrical workers in many cases, because you find that particularly safety equipment like actuating bars and insulation and trunking lids and ingress of God knows what in there is a direct result of the people that are actually maintaining the equipment itself. So sorry to go off on a rant on that, but if you take a proper look at audit of the electrical system, these things will come up. And of course, as my previous slide suggested, it provides knowledge to workers. In the guide, I put forward various things, but these are a couple to back up my point about improving the electrical safety management. Things I mentioned about the control panel audit. Doesn't take very many minutes to do, actually. It's a straightforward tick list. It's what comes back from that, which is, the actions that you take to make sure that those things are put right. And as you can see, there's very little on that on the right-hand side to do with arc flash. The vast majority is about the equipment in arc flash, and shock hazard, I beg your pardon. That's where most of the issues are going to create the conditions for people to get hurt. And on the left-hand side, there's when using the tools that we've designed, that's the output from the incident energy tools to be able to have a prediction of the arc fault at that point, prevention, section, process, and protect. So that's come to the end of that section, so we've gone through 10 reasons for calculations. It could have been 12, but I cut it down to 10. I think we left imperial measures back in the 70s, if I remember, so I made it 10. I hope you found that informative. But I'm just going to go on to put a couple of exciting announcements out there. And the first one is the IET Arc Flash Working Group, which I've been working on. Has created a new IET fact file, which will be going live very shortly. And basically what it is, it's a structured approach to performing risk assessments for electrical power equipment and ensuring safety. And you can see there that little symbol of predict, prevent, process and protect. What that's based on is firstly, the prediction of the hazard, doing the calculations, prevention and minimization to prevent the hazard from causing harm. Process policies and procedures is the next item. And then finally, if there is requirement for PPE, that we're protecting against residual risk at that point, and hopefully not putting people into restrictive PPE. So that's publicly available very shortly from www.theiet.org, and just simply search for fact files on there. But we do talk in there about if we come back to the prevent area, we're talking about dead working, the elimination of live working as the removal of the hazard, automatic disconnection of supply by early detection and rapid de-energization of the supply to cut down the amount of damage. Through equipment design, lots of innovative stuff out there right now, but to reduce the likelihood of arcs or to dissipate arc flash energy safely. And I know that there are people attending today that are in, looking at innovative ways of providing the equipment design to protect people. And then finally, operationally, you reduce the likelihoods of good system operations, audit and maintenance. And I've been so pleased to be part of that working group, which is comprised senior experts and regulators from the industry. So it's going, as I say, it's going to be released very shortly. I hope you'll catch up on that, and it's very readable. The other thing that I'm very excited about is coming back to the European Art Guide, and we know that the guide is an online practical assessment tool for the European engineer. It's primarily designed to evaluate and manage dangerous levels of arc flash incident energy and electrical distribution systems. Whilst the guide's based upon European Council directives, there are specific references in there to the United Kingdom and also our closest neighbour, Irish regulations and standards as well. So as laws and regulations evolve, then the guide will be updated accordingly. And I hope you get to see that. It comes not only with a guidebook, which is about 200 pages, to explain what to do, if you like, what I would do if I were you. And I'm going back on my experience and pulling on the experience of very many people in the industry as well from a peer review point of view. But these are the sort of calculators that you can expect in there. This diagram, if you look at A, they're all based on IEEE 1584. There's calculators for the basically for incident energy, the arc flash boundary, and as I said earlier, even if you don't want to know about that, you know, I think you ought to know about how much current would flow in an arc, and that will be telling you that information in that simple calculator. But it also accounts for contributions from motors as well. So if you've got a plant that has a lot of motive power on there, it'll account for that too. There's also LV circuit breaker calculator. There's also one for fuse charts, which give you the incident energy against the popular fuses within the UK and Europe, according to IEC 609-28-2, and also devices below 125 amps. They're also, not everything's included in those calculations. And by the way, I've got to say clearly we are looking at thermal hazard here, and there are other hazards that aren't covered by the calculations. They'll give you a good idea whether, you know, whether this is more likely or not. But if you're looking at oil-filled switchgear, for instance, oil-filled switchgear, if there's arcs in that aren't cleared well, that can lead to catastrophic explosions and damage, and has resulted in fatalities, of which I know of personnel that have been killed in those positions. So on to the next one, theoretical papers. For DC incident energy, we've got a calculator for that. It's not in the same mold as the IEEE 1584, but it's based on theoretical peer-reviewed papers, and as is blast pressure. And in bottom left-hand corner there, there's also in Europe, there's German box test algorithm, which is based upon the testing of PPE to what we call the box test. And out of that, an algorithm has been created, which is based on theory, which is also included. And then finally, supporting calculators. In some cases, we need to know about fault current. So there's a calculator there to allow us to do that. Also, there's calculators to allow us to pick up the popular HRC fuses, as well as IDMTL fuse time current curves as well. Right. And what I've done is to tier the approach as well. And if I could just explain, at the bottom, tier 3, that is actually, you would only need to know the fault level to make those calculators work. So you'd need a minimum fault level. So I suppose it's a case of, you might not know what the exact fault level is, but you do know that it's not below a certain figure. So it's aimed at lower level faults in that respect. Tier 2 circuits, where you would need the actual fault level, but you wouldn't need the time current curve. And tier 1 circuits, like the IEEE 1584 calculator, you will need a time current curve, and you will need the actual fault level. And as I said, there's our supporting tools that might help you to get to that point. These are some screenshots. As I say, these are going through the final throws now of quality checks. But in this case, this is the instant energy calculator. The first window at the top is what you would normally see. If you want to put manual entry, you can put a standard generic equipment class, but you can put manual entry in as well, which is the next one down. And then finally, the multi-fault levels as contributions as well. And at the bottom, they're the results that you get from that. This is a tier 2 circuit breaker calculator. I'm very excited about this. A lot of work's gone into it to try and allow people to do dynamic risk assessments. We've achieved that with fuses, but circuit breakers are a different thing. And basically what we've done is to create the conditions where if a circuit breaker disconnects instantaneously based on its instantaneous pickup level, then it would produce an instant energy level based on the prospective short circuit current and the arcing current at that point. If it fails to clear the instant energy level, it defaults back to a 2-second disconnection time. So at least we've got a factor of safety there. But we've based it on something like 8,000 common miniature circuit breakers, air circuit breakers, and also molded case circuit breakers as well. The tier 3 type devices are where we've got simple fuse charts. And if you look on this particular fuse chart, which is an actual one, we've got 2 zones there. There's a fast acting zone, which is above 6,000 amps of prospective short circuit current. And we know that if it's in that zone, we know that it will disconnect fairly rapidly, and actually the instant energy level will be below 1 calorie per square centimetre at a working distance, in this particular case, of 450 millimetres. But there are various scenarios and various fuse charts that will be provided as well, you know, for differing scenarios. So that will be coming out. But the other thing is a danger zone. It also tells you on the left-hand side that pink block there is where it's below 6,000 amps that it will take longer to clear, and up to a maximum of 2 seconds. That's the sort of incident energy level that you could be getting in that particular case. So it's based actually on the same principle as shock protection. You know, you need so much current, prospective short circuit current, to operate overcurrent protection to reduce the time to trip to as low as possible. This is one of the supporting calculators that I told you about earlier. In this case, you've got a choice transformer or you can delete it if you want. And then 3 switchboards down, you can calculate the fault level at that point if you want. And it's based upon generic transformers and cable information and cable installation methods. But the outputs from that will give you prospective fault current. It'll also give you an X/R ratio. It'll also give you a minimum prospective fault current in accordance with IEC 60909, and also the maximum prospective fault current. And those last 3 items, you'll need those if you're using the German algorithm, DGUV algorithm calculator. And we've also got supporting calculators for time current curves on the left-hand side. They're all the range of fuses for either BS88 or NH-DIN fuses. And you can simply, on the left-hand side, just enter the specific input time, or you can enter the specific input current or arcing current, and that will give you a disconnection time. And on the right-hand side, there's IEC IDMT time current curve calculators as well. So that's a quick run through those. What I would ask is if you like what you see, if you want to pre-register, that's a pre-registration address there. It's ea-guide.com/pre-register, and from that you will get access straight away to the first part of the book. That's 130 pages, first 7 chapters, and with calculators on the right-hand side, these are the items in blue there. What will be available in there are specific areas, like quite an in-depth section on data collection, what to look for, and how to read relays and all this sort of stuff, really down to some detail, and also what to take out. How do you set this up safely from a data collection point of view, whether you're a service provider or whether you're actually doing the data collection for yourself. How do you set a safe working system up? I've done this for a lot of years right across Europe, so I think I know what I'm talking about in that regard. So that's quite a valuable section, I would say. Also about electrical duty holders where you own a network, what should you be looking for, and also where you have to ship things out. What about choosing contractors and so on. That's all in there. Service provider contracts, if you're going onto a site, you've got minimum information on that particular site. That's where that chapter's aimed at. Electrical utilities, I did a big piece of work for one of the major utilities in Europe, and I've based a lot of that section on that, with their blessing as well, I might add. My favourite chapter is myths and mistakes, and I've based that on too many years in the industry, seeing exactly what mistakes people have made and some of the myths that abound around arc flash as well. And complex software guide. I know there's people that manufacture and are vendors for complex software that are on this, and welcome to you. This guide explains what to look for, when you're choosing software for yourself. And the chapter 14 is to help you to operate all the hazard and severity calculators. It's basically the instructions. And following today, I've got a section on why do arc flash calculations, and that's what that particular chapter's about. And finally, on rules, codes and legislation, there's even a section on Brexit for those that live in the United Kingdom. So that's it. But before you ask me questions, I'll ask you some, if that's okay. If you're an electrician that's watching this, or a refrigeration engineer, or a maintenance technician, or any other kind of electrical worker, ask this: do I know what might occur should things go wrong when I'm about to carry some voltage measurement or some commissioning checks within this panel? So do I know what might occur if things go wrong? If you're a manager or a duty holder responsible for putting people to work on electrical apparatus, this is a question I've got for you. Do I know whether there's the equivalent of a tiger or a domesticated cat lurking within my switchgear and control panels? And finally, for you designers out there, ask yourself, will my protection, will the arrangements operate quickly, safely and effectively for an arcing fault? Or, and I'll leave you with this now, will it operate sometime next Tuesday? So thank you very much indeed for listening to me. Hopefully we've got some questions to answer.
Yeah, well, thanks for that, Mike. Yep, that's been quite enlightening. We'll hand over to Linda now to manage the Q&A.
Yeah, you've got one or two to answer, Mike. David Eastwood, what is the preference in calculating the arc flash on the primary protective device or upstream backup protective device?
I take it, David, we're talking about where you're working within a control panel, and perhaps there's a device there at the control panel. I would normally look upstream, as you referred to it. I hope I've got the question right, but it refers to the upstream device, the line side, if you like, which is often referred to. If there's a fault on the equipment, I've seen situations, I can show you photographs of where a fault which has occurred on the lines, on the load side of the incoming device, has actually migrated to the line side. And that's in a Form 4 panel, by the way. It's a low voltage panel. And, it's actually migrated. And the reason it's migrated because there's been low level arcing occurring within in this particular case that I'm referring to, within a switch fuse. And because the monoblock casting for the switch fuse was actually cracked because some idiot tried to force an oversized, physically oversized fuse, that is, a physically oversized fuse into the carrier. It cracked the carrier and it caused bad connections within the monoblock itself. And so all the time you've got the products of combustion from that. And when that spread to the line side, to the load side, it then migrated to the line side. The reason I know that is because all three fuses blew. So we know that it started on the load side, if you like. So we know that happened, but it migrated. So I would normally look upstream for protection in that case. So I hope that's answered your question, David.
Hashim has asked, is the overprotection device or RCDs detect and clear the arc fault? Is there a separate arc fault device required?
Could you just do that again for me, Linda?
Yeah, of course I can. Yeah. Is the overprotection device or RCDs detect and clear the arc fault? Is there a separate arc fault device required? I think I've said that right.
Yeah, I think you might be referring to arc flash detection devices. It's something which is being debated heavily at the moment, and more so because of Grenfell Tower. For people outside the UK, it's a tower block that burnt down in London. You know, killing 73 people. I think it's 73 that were killed there, and what caused it was a fault within a refrigeration unit, and it's thought, it's not conclusive, but it's thought that it was a serious fault within a connector, which created the conditions for the fire. And RCDs wouldn't pick that up if they were connected. But arc flash detection devices, they pick up the signature of an arcing fault, the electronic signature, and they disconnect equipment accordingly because of that. They've been around for years, by the way. You know, I mean, I think probably 20 odd years, and we're sort of catching up within the UK. But we're always fairly conservative, I think, with anything that comes out on the market. But there's some debate whether that would have actually prevented that particular disaster and other fires elsewhere. But I'll be listening to the experts in that respect. But yeah, an arc fault detection device is very much for final circuits and usually low-level faults. But I'm quite sure that arcing faults have been responsible for many fires, both within industry and also domestic properties as well. Okay.
Yeah, I'm hoping you can hear me okay, because I keep getting a flash up saying that my internet connection is unstable. So Keith has asked, if you do these steps to remove the need for the PPE, won't the PPE still be required? Or do these steps completely eliminate the risk of an arc flash?
No, you can't totally eliminate, you know, an arc flash risk in that respect, as you can't eliminate, you know, shock protection hazards through the means of protection. You know, when we think about protecting against shock, there's plenty of occasions when RCD devices haven't operated. You know, and also overcurrent devices where they're on larger equipment. But yes, I think if we go through the proper steps, and I showed you that dynamic risk assessment form earlier, so the 4 Ps model that are displayed in the IET fact file, which is going to be published very shortly, and the guide that I provided, if you go through that, the reasons for PP in every case are removed. But don't forget, there are going to be many cases where you can't reduce the incident energy level no matter what you do. You can't reduce it to below 1.2 calories per square centimetre, as I suggested earlier. But you could probably do it for 90% of the cases, and that I'm sticking my neck out on that, but that's my experience. You know, you can actually reduce it below those levels by good engineering practices. So the other thing that we do mention in the fact file is that there are instances where you ought to be wearing certain PPE. If you, for instance, if you're working in control equipment where there is a arc flash hazard at that point, even if it's 0.3 of a calorie, you know, at the head and torso, they, you know, the factors are nearer that you get to the arcing source, the higher the incident energy level is going to be, you know. So, and it's exponential as well, you know. So half the incident energy and it quadruples, you know, bit less than that, but you know that you can see where I'm coming from. So if your hands are on the probes for a voltmeter or something like that, and there is a fault at that point, there's a flashover, it might only be 0.3 at the head and torso, but actually hands it could be very much higher. So my thoughts on that, and they have been for many years, is why wouldn't you wear some gloves, you know, over gloves and voltage protection gloves at the same time. You know, I started off life as an electrician, and I've had to take thousands of hundreds of classes involving thousands of people on electrical safety, and I've been through all the reasons, you know, perhaps dexterity and so on, that people might put up for gloves, but that's not something that I think should be a reason for not doing it. And sorry, I'm rambling now, I think, but the other thing is I remember seeing a situation where somebody got burnt on the hands. They were doing something very silly. They were plugging on a circuit breaker onto a quite high specification board, but it flashed over in the hand. And if I'd have done the incident energy calculations at that point, it's likely that there would have been very little incident energy at his body, but it was very much higher at his hand, and it caused a burn to his hand itself and his forearm, and he went into hospital just to accident in an emergency. They cleaned it, dressed it, and sent him back home again. He went back into work the following day on so-called light duties, and by the afternoon he started to feel unwell, and he readmitted himself to the accident and emergency unit, and they kept him in for 7 days, believe it or not, because of what I believe was sepsis. A good mate of mine is an ex-senior manager from the health service who used to run a burns unit. So that's what I believe happened to him. So it could have killed him, actually, if you believe, you know, 7 days in hospital is not something we do very often, you know, and to recover from, you know, blood poisoning like that, it took him all that time. So I think hand protection, regardless, is something that people should be wearing.
And have you done any work to identify the arc flash risk in EV battery packs or for lithium energy storage?
Yes, I have. I hope that's not all you want to hear. I've worked for a major manufacturer and tester, actually, and I you know, based down in the south of England, and they wanted me to go in there and have a look at their safe working system. So yes, we have a good handle on that, on the electrical flashover, as I was looking at shock risk as well, by the way, down there. But yes, we have had a look at that. And as I said earlier, the means to calculate the incident energy on systems like that is restricted to peer-reviewed papers, and that's what we used in that case to try and quantify the amount of incident energy.
And how does network impedance affect arc flash calculation?
Oh. So is that a secondary question there?
Yes.
So how does it work in protection?
How does network impedance affect arc flash calculation?
Oh, sorry, sorry, I did miss the first part of that. Say that again.
How does network impedance affect arc flash calculation?
Yeah, good question. Thank you. Yeah, I've got that now. Yeah. Well, impedance affects arc flash calculations in exactly the same way as, you know, for arc flash as it does for shock protection. So impedance happens to be your enemy when it comes to arc flash protection. You might be saying, well, you know, doesn't low impedance mean lots of current? You know, what happened to I squared T? What happened to good old I squared T? Well, I squared T still works, it's still there. But as I demonstrated earlier, that if you reduce the current by a few amps sometimes, or perhaps more, you know, the time to trip could be massively impacted, which means that you reduce the current, so the I squared bit is not reduced that much, but then the T is through the roof. So the amount of energy that's let through in those circumstances is, you know, can be enormous. And quite often that's the case. I mean, a lot of the high instant energy levels that I come across in industry are, you know, on LV equipment that hasn't been maintained properly, where we've had to look at 2-second disconnection times, and as a result, the instant energy downstream from that has been quite high. So impedance is vital. It can be your enemy as well as your friend. So if you've got low impedance, even though you've got very high fault levels, you know, the fault, you know, particularly for HRC Fuse that I've described there, they can disconnect a dangerous fault very quickly, providing that the impedance is low enough to allow enough current to safely rupture that particular fuse, or to disconnect that particular circuit breaker. Okay.
Okay. There's quite a lot of people asking where the calculators can be accessed, which I think you've already mentioned.
Well, it's there on, you know, on that screen. I hope you can still see that. Just go on to e-guide.com / pre-registration. And as I say, we're going through the final throws now, and the calculator should be up and running shortly, so that you know, you can start doing that. There are, I mean, don't forget, if you were just looking at IEEE 1584, you can buy that, you know, from the IEEE. I'm not quite sure of the web address, but that not only gives you the calculations, but it gives you all the theory behind it, as well as other quick means to calculate instant energy and so on.
There's a couple of people have mentioned that the pre-registration that you mentioned, the ea-guide.com pre-registration, is coming up with an incorrect address. It should just be ea-guide.com /registration. So I'm guessing that has changed.
Oh, have I?
That has changed in times.
Yeah, probably. That's a blooper on my part, by the sound of it. So it's spelled differently early on. Is that what it's saying?
Yeah, it's just, instead of pre-registration at the end, it's just registration.
Oh,
so people have mentioned it in the chat, and Roger Greenwood has also mentioned it as a question as well.
Well, thank you so much for that, for highlighting that for us. So yes, registration's fine, but if you go in there, you can pre-register as well.
That's good. Neil Wynn has mentioned, I noticed you had a model drop-down box on your calculators. How big is the database?
The fuse models. It's we're looking at something like 8,000 devices that have been put in there, and basically what it is what we've looked at is created a model and then made sure that each one of those devices that are listed actually conforms to the model itself, because there are some that don't, and the ones that don't aren't on the list. So you know that there is a means to validate that directly. You know, so if there's one that isn't listed, you can validate it directly.
And what do you think about motorised circuit breaker racking devices in relation to HV circuit breaker operator arc flash risk reduction?
Well, I think that remote operation has got an absolutely ideal place, particularly where you're looking at existing equipment, you know, in industry that's been around for a good few years. Not that you're ever going to countenance people switching unsafe equipment, in my view. But there are times when equipment is has been put under what we call suspensions of operational practice, where people cannot operate it because somewhere else in the country or the world there's been an incident on that particular model of equipment. And if there has been, it may well be that one of the suspension of normal operational practice might require remote operation of that particular equipment. So either you isolate it from elsewhere, or you use a device like a motor operating device to plug on to rack out the equipment, or to even operate on and off of that particular circuit breaker. So definitely got a place, you know, within the prevention strategies to make sure that people are not in harm's way where there's any question marks whatsoever over equipment.
There's one or two people posting messages, posting questions over into the chat function. I don't think we'll get a chance to cover all of the questions tonight, but we can download them and then send them over to Mike, and he can drop you an email back to answer them. So if you want to send those over into the Q&A session, and then we can download those. We can't actually download the chat area, so if you can send those over. And there's some quite long-winded questions as well, Mike, that I think you're probably better just reading through.
Well, what I will say, I'm always very happy to answer questions, or you know, or you know, something I do learn from any remarks or whatever, you know, any comments. I'm very happy to receive them, you know, particularly from professional colleagues at all times. So if there is anything in that regard, you can always send it to my email address as well. I'm quite happy to give that out. It's just simply Michael Frain. It's not Mike Frain, but Michael Frain, all one word. The next bit's easy, at AOL.com. So it's Michael Frain at AOL.com, and I'll be more than happy to answer those. If there's any questions left over tonight, and I can't stay on for a great deal of time, I've got to say, answering questions right now, but you know, I will answer any other questions and put a Q&A crib sheet back up onto our website and the IET website, so you can view that at a later date and see what other questions have been asked.
No, that's good. There's quite a few left unanswered, Mike, so we're probably better off downloading them from here.
Excellent. Yeah.
So over to you, John, to wrap up.
Yeah, well, thanks for that, Mike. Thanks for that, Linda. We tend to measure how good a presentation is by the amount of Q&A that we get and the amount of interaction we get on chat. And as per usual with Mike's presentation, we've had a load of it. There's been chat all the way through. Real good sort of exchange of ideas, exchange of views coming through on chat. A load of questions. And like I said, Mike, we'll get around to them. We'll answer them afterward. But I think there's a few key points to pick out of this. And it's similar to the electrical safety management stuff. And what Mike's been putting forward is all about doing the basics well, understanding your risk, understanding the sort of magnitude of your risk, and understanding how you should manage it. There's key issues there about your own personal competence. Do you understand enough about the risks that you carry? And I know we've talked about this in the past. I mean, I've had personal experience of an arc flash and catastrophic equipment damage. And it were always on the LV stuff. We tended to sort of look at the HV stuff and understand the risks with the HV stuff, but I think we're always a little bit complacent with the LV. And it's certainly something to think about that. And also about how you pass that knowledge on to others. I think Mike's made a good point there as well. You might be the duty holder. You might not be the duty holder, but you might have people in commercial, you might have people in senior management, you might have people in operations management that are handling some elements of the risk. And are you doing enough, if you like, to sort of get that information across to the non-technical people to understand the risk that's being carried? Because I think in the past we've had issues, particularly when we've had older industries, more mature industries with type of switchgear that can sit for a long time, where asset replacement and renewal has not been carried out because I don't think that the senior management have really understood the risk that they've been carrying. So there's certain things to think about in that respect. So pick out, I mean, from my point of view, the learning points, spread the news, identify, understand your hazards, understand your own limitations in terms of your knowledge. You've got plenty of people around you that understand this subject. Mike is obviously an expert on it. Get in touch. But do the basics well. A good electrical asset management is good safety management. And I think, again, Mike's touched on the point there about understanding your asset, understanding what's going on behind the scenes with your asset. And I know we've talked about this offline, Mike, but it's a real good measure is when you look at your asset, what does it look like? How are you managing your asset? Are you ankle deep in dust in your substations? That's a bit of a problem from us ex-steelworking types. But it is a really good indicator of how well you're managing your assets and how seriously you take your electrical safety management as to how clean your situation is, how well protected they are, and how everything's been sort of maintained over the years. So we'll wrap up there in terms of Mike's presentation. Just a few notes on South Yorkshire Network moving forward. We have a presentation coming up that's looking at level crossing innovations in the UK. That's going to be in September. We've got a slot and we're currently debating a number of different things that we can drop in before the September presentation. But if you want to speak on any subject on behalf of the South Yorkshire Network, as you can see, we get worldwide coverage on these presentations now. So if you do want to speak, do get in touch with us, grab us on LinkedIn, contact us through the IET. But if you want to hear about a topic, or there's any topics that you want to cover, or anything you want for us to investigate, if you like, to put a webinar on, get in touch with that as well. So don't be shy in terms of coming forward. But the next event that we've got actually in the diary will be around about September time. Just finalising the date now. That'll be a joint event with the South Yorkshire Local Network and the Railway Technical Network, and that'll be covering level crossings and general innovation around level crossing. So with that, I think we'll wrap up. I'll thank everybody for their the time and for stopping by, and we'll speak to you soon. Kevin, 1, 2, 3. Are you clear, Linda? Do you want to say something?
No, I'm fine. I was just saying goodbye.
Yep, great stuff. Again, thanks everyone. Bye.